Chapter 25, Statistical Thermodynamics, Section 25.2, Translational Partition Function and Energy. The average translational energy of the particles can be determined given the translational partition function using the following equations. The average energy is negative dln(q) over d beta. The average energy is kbt squared times dln(q) over dt. The average energy is kbt times dln(q) over dln(t). So we just need to find out the expression of the translational partition function in terms of beta or t, and then we can plug in the expression of q into these equations to get the average energy of the particle. For quantum translation in a one-dimensional box with a length of a, we have the energy levels here. The epsilon 1d translational energy is n squared h squared over 8ma squared. H is the Planck constant, m is the mass of the particle, a is the dimension of the box, n is the quantum number, n is 1, 2, 3, 4, integer numbers. Now let's look at q, the partition function of one-dimensional translation. It's the sum of the Boltzmann distribution functions e to the power of negative epsilon over kbt. Here, this epsilon is one-dimensional translational energy, and that's n squared h squared over 8ma squared over kbt. So we need to evaluate this sum. This sum is approximately this sum. I only changed the index here from a 1 to a 0. So over here we have all those infinite number of terms from 1 to infinity. Over here I just added 1 over here. So this is a huge number. This huge number is approximately equal to itself plus 1, because when n is 0, this exponential function is 1. Again, if you have, for example, 10 to the power of 24 here, it's approximately the same as 10 to the power of 24 plus one additional term, 1. Now let's look at this one-dimensional translational partition function. It's written as a sum over here, but now it's written as integral here. So how can we go from sum to integral? Well, if you look at the integral, well, the integral value is simply the area under a function curve. And the area under a function curve can be decomposed into many bars, right, with a width and height. And if we have a really large number of bars and narrow enough bars, we can see the sum of the function is approximately the same as the integral of that function. So that's what I did over here, from here to here. What I'm doing is I'm trying to approximate this sum by using an integral. The reason is it's very difficult to actually get the sum, but it's easier to evaluate this integral. And again, this approximation is quite reasonable because we're simply looking at a infinite number of terms with a infinite number of bars and with very narrow bar width. Going from here to here, we simply used the properties of Gaussian functions. They are even functions. That means the integral of a Gaussian function is simply just 2 times the integral of this Gaussian function of just one side. You can always divide a Gaussian function into 2 parts, from negative infinity to 0, and then from 0 to positive infinity. Alright, so this is from over here 1/2 of the entire Gaussian function to the entire Gaussian function. That's why I put 1/2 over here. We just need to evaluate this. How do we do that? We need to use a variable substitution. We simply set alpha to be h squared over 8ma squared kbt. So over here, h squared over 8ma squared kbt is alpha. Now we get this equation. Alright, and we're not done yet. We still want to further simplify this equation as well. We will just put a square root of alpha here, and then divided by square root of alpha here. The reason is we're about to set a new variable to be equal to square root of alpha times n, and then this is going to be e to the power of negative that variable squared. So again, the one-dimensional translational function is 1/2 of this integral of this Gaussian function from negative infinity to positive infinity. And I multiply this n by the square root of alpha, and then divide the square root of alpha here. Now I set z to be the square root of alpha times n, and then this one-dimensional translational function is simply 1/2 times square root of alpha, and we just need to integrate a Gaussian function from negative infinity to positive infinity. This integral is the square root of pi. We can prove this if you know how to convert the Cartesian coordinates to polar coordinates in a two-dimensional space. So we can prove this part squared is actually pi. But let's just use the conclusion here. This integral is the square root of pi, and therefore the one-dimensional translational function is the square root of pi over 2 times the square root of alpha. Alpha is defined to be h squared over 8ma squared kbt. And we clean up this a little bit, we get the square root of 2 pi m kbt a squared over h squared. So it's just algebra from here to here. It's simply algebra. And now we get this expression for one-dimensional translation. It's the square root of 2 pi m kbt, and then multiplied by the length of the box over the Planck constant. For a quantum translation in a three-dimensional box with the psi length of a, b, and c, the 3D translational partition function is the product of the three individual one-dimensional translational partition functions. So over here, this 3D Q is equal to this in the, for example, x direction, and then this partition function in the y direction, and then this partition function in the z direction, and then we just do the multiplication. We have now 2 pi m kbt to the power of 1.5. And then we multiply a, b, and c together over h to the power of 3. And a times b times c is simply the volume of the three-dimensional box. So now the three-dimensional translational function is 2 pi m kbt to the power of 1.5 times the volume over h cubed. The three-dimensional translational partition function is written as q superscript 3D and subscript translation. This is proportional to the volume of the container, and it's proportional to temperature to the power of 1.5. Now let's use the partition function to get the average energy. The average three-dimensional translational energy of the particle is kbt squared d ln q over dt. We're going to use just this equation out of the three. We can use any one of the three equations. It can be d ln q over d beta. It can be d ln q over dt. It can be d ln q over d ln t. So just whatever you do, just use the equation, the corresponding equation exactly. Right now I'm using d ln q over dt, so this has to be multiplied by kbt squared. If you do d ln q over d beta, I think you need a negative sign. If you do d ln q over d ln t, the result should be multiplied by just kbt. So anyway, I'm using this equation and this equation. So either way, you can use either one of these two. You can use d ln q over d beta times -1 as well. But right now, it seems more convenient just to do one of this. The average energy is kbt squared times d ln q over dt. And now look at this function. This function contains temperature here. But that's pretty much it. So we can decompose this logarithm into the sum of two logarithms. This logarithm is the logarithm of a t to the power 1.5 plus the logarithm of everything else. So over here it's just a constant times t to the power 1.5. and that's why I can separate this two here. And now look, the logarithm of everything else is independent of temperature, so this derivative is just 0. We just need to look at this one, and when we look at this one, we have this expression. And how do we do this? Well, it's pretty simple. The logarithm of t to the power 1.5 is simply 1.5 times ln(t). And the first derivative of ln(t) is 1 over t. So that's why we have 1.5. We have 1 over t here, multiplied by this kbt squared. Now we get 1.5 kbt. The average translational energy of the particles is 1.5 kbt. I used the particle in the box model and get this expression. The average three-dimensional translational energy is 1.5 kbt. The molar three-dimensional translational energy is this. Okay, so it's just Avogadro constant times 1.5 kbt. We get 1.5 RT. Don't forget that we made some assumptions in the derivation. We're assuming those are free particles in the box. That means they don't feel any attraction or repulsion. That means we're dealing with ideal gases when we derive this. Okay, for ideal gases, no attraction, no repulsion. They are considered free particles in the three-dimensional box. The average translational energy is 1.5 kbt, and then the molar three-dimensional translational energy is 1.5 RT. And what if there is attraction or repulsion? Then we need to modify the expression of the energy levels, because the energy is going to include both the kinetic energy and attraction and repulsion. Again, R is simply the Avogadro constant times the Boltzmann constant. Similarly, we can derive the one-dimensional translational energy as well, per particle and per mole. So really, you just need to use the one-dimensional translational partition function here. I think it's the square root of 2 pi m kbt multiplied by a over h. When you do that, you'll get just 1/2 kbt. Alright, so in that case, one-dimensional translational energy has an average value of 1/2 kbt. The molar one-dimensional translational energy is going to be 1/2 RT.